expensive software and firmware within the context of a real-time execution loop, which I will talk about, and that loop is now going to protect the host operating system. But it does, what is required, of course, is that you have expertise relative to that host operating system, whether it's Linux, Solaris, BSD Unix, Vertex. You need expertise in the target operating system because, after all, you have the firmware and the control loop that's running has to have some notion of what the target execution environment ought to behave like when things are working correctly. And then it has to be able to detect when things are not working correctly and to take effective action to fix it. And it has to be able to do that in real time, which is critical for those tasks that cannot be interrupted. This is not a technology that's meant to protect your Warcraft game or whatever else you play on your desktop. It's not meant for that. It's meant for production systems.
Can it be used for that?
Excuse me?
Could it be used for that?
Of course.
Okay. It would just be ludicrous to do that.
It would be expensive. I don't know if it would be ludicrous. I think it would be fine as far as I'm concerned.
Expensive is sometimes okay.
Okay. So this is a box, but I don't want to waste your time with the box so much. There's a model that we built, a prototype for demo purposes. Okay, so now we're going to talk about restoration of information systems through detection and reaction. So the philosophical basis for our control loop, our real-time control loop, is based on something called the OTA loop. The OTA loop had come about as a consequence of a work that was done by an Air Force colonel, Colonel John Boyd. And he was nicknamed 42nd Boyd because that was typically how long it took him to kill opposing fighter pilots. And there was a standard bet that if anybody lasted longer than 40 seconds, he would give them $100. And this was in when they did that red flag type training and so forth. But he also flew in, I think, Korea and Vietnam, chasing MiGs. And so he's a phenomenal fighter pilot and also engineer. He was he was the chief design motivator for the F-16, which has really outdone any other fighter plane for years. In fact, it's still very difficult for pilots to fly that plane and remain conscious if they push it to its limits. So essentially, this loop says, I'm going to make observations. Then, dependent upon my orientation, I'm going to generate a course of action, and then I'm going to make a decision on that course of action, and then affect that course of action. Now, it was designed for a human, so there's an implicit learning. We have augmented this loop with an AI component that says, essentially, I detect through sensors here, I detect through sensors the state of my target machine. And then if it's something that I know how to deal with, I will take care of it here and generate a course of action. If it's not, I pass down the state of the machine and ask the AI engine, I give it a goal, and I then ask the AI engine, how can I achieve that goal? The AI engine has knowledge of it, of the domain in which we're executing, and knows what we can do. What kinds of actions can we take? For those actions, what are the necessary preconditions? What are the effects after we execute that action? And what collection of actions, in what order, will lead us to the goal that we want? Once that is known, it is fed back up and goes through, and it's acted on and cataloged. Now recall that we had those two Ethernet connections. One of those connections can be used to connect all other machines that have this technology. So a zero-day attack that the AI component develops a course of action against, both the initial state and the course of action can be spread through the network in near real time. So as soon as detected, a course of action is developed, and then the response is spread to all the other machines connected in that network as quickly as possible.
You're talking about that AI engine. That engine was the training or the system's made, or is learning on the going?
It's learning in the sense that there's an initial state and a goal state. So we present the initial state and the goal state, and then it generates a set of actions to attain the goal state from the initial state, and that's fed up. That information is then collected and stashed away in a set of, we'll call them protocol actions, so that if additional states, if in the future a state reappears, we will know what to do and we won't need to go through the AI component. So it's learning in that sense.
Oh, so it remembers its successful decision. Okay, I see.
Now there's another set of actions. Excuse me.
Any limit to how much memory you can accumulate?
Well, there's a two. If you have
like
a two.
In other words, if you take a card out of a 5-year-old machine and put it in a brand new one, will it be more intelligent than a brand new card?
Well, remember you can connect a disk to it.
Right.
So if you're storing that information on the ancillary disk, you can have up to 2 terabytes, right? And more as the disk technology advances.
Are you guys planning on sharing? Are you guys planning on sharing successful decision tables with your clients as you progress?
Well, the decision tables belong to the clients, not to us.
Oh, right. So the clients will be.
We'd have to decide whether or not they want to form a group and share.
Okay, so your model is all independent decision making. Right.
Unless there's a group that wants to share information.
Right. So that's customer. All right. Cool.
Yeah.
Interesting.
I mean, you can imagine if someone is spending.
I think like antivirus makers, that definition.
There's a lot of information that makes sense to share, but there may be situations where clients say, no, thank you, I'd rather not share anything.
Okay.
Okay. So essentially, here is a big picture of what goes on. Now, what we haven't talked about is what is the magic in all this, and it's these things that we call hardware mediators. So one of the first ones I want to talk about, and there are slides, but the slides don't really show you. Let me jump to it anyhow. Let's see. So we talked about him. This is the secure disk. Let me get to. All right. So this is a simple block diagram, but very significant. So on the motherboard, there's something that's called a host bus adapter that sends commands to your host disk. Now this is the host disk, not the secure coprocessor's disk. And if you want to write something to the host disk, the operating system writes to the control registers here, usually the disk device driver. Now, this is pretty deep inside the bowels of the system. So it's very low in the OS, and it's even lower because once it writes to these control registers, the host bus adapter emits a packet to the host disk that on the disk there's something that's called DCL, device control logic. And there's a processor on that disk that understands the packet that is sent to it. That packet is not something that is constructed by the software on the host system. It's constructed by the host bus adapter. So we're working now, we intercept those packets, so now we're working below the machine code. In other words, we're lower level than the machine code on the host machine. For example, a practical use of this technology. I think it's pretty well understood that if you write protect a disk, what that means, how that's implemented, is that the operating system will not allow a process or a device driver to write to the sectors belonging to that file. That's all it means. There isn't any hardware magic. It's all software. So now imagine that the operating system itself is what has been subverted. That means all those protections evaporate. They don't exist any longer. The malware can write to wherever it wants. So with our approach, one of the simplest, straightforward uses of this technology is once you configure your machine, you identify those files that you don't want changed. For example, the operating system files. You don't want them changed unless there are some special conditions. Maybe you're doing an update or something. But typically, you don't want them changed. What the secure code processor does is it goes in, parses the path name of those files, and identifies each sector belonging to the protected files. Now, at a much lower level, and this is what we call autonomic response. Now, in the human body, an autonomic system is the thing that controls your heartbeat, controls your breathing. So at an autonomic level, the secure code processor, through its mediator, will take action without having to have been directed to do so. So in effect, the SATA mediator is loaded up with sectors that are not to be written to. When an attempt is made to write, before the attempt is made by the malware, it hits the host bus adapter, gets to the SATA mediator, it matches a protected sector. And then it is up to the users of this system what they decide to do with that event. So you can imagine if it's a forensic situation, someone might want to stop the write but record what was going to be written. And then by tying back to other mediators, go back and detect the process that attempted to do the write. Work backwards. Now, the beauty of this approach, of course, is that it's not signature dependent. It doesn't matter who tried to write to a protected sector. We can detect zero-day anomalies just by their misbehavior. We don't need to have seen it before. So it can be stopped cold. Okay, this just talks about Linux file system data structures. And this is by way of if anyone is curious as to, how do you find sectors that are associated with a file. Well, when you take directory listings, there are names, and then the name of a file is just a string. The important thing, though, is that the name corresponds to an inode. And the inode is the data structure in Linux that contains all of the information having to do with what sectors that information corresponding to that file, what sectors are assigned to that file. You buy a system if you decide to use, let's say, a Windows system, then the protection software, of course, has to know about Windows. It has to know about the Windows file system in order to protect it. So you have to buy the system built for Windows or built for Vertex, if it's Vertex, and its file system. So yeah, it has to know about the file system that you're about to protect.
Are there any file systems in Linux it doesn't currently do?
Any what?
Are any file systems in Linux that you don't currently work with? HT4, I assume.
We are experimenting with only this file system right now.
Right.
But when
Does it operate
someone
at a block level?
sectors.
Yeah, I know, but like in the Linux kernel, I think there's a block layer. File system layer.
Yeah.
Do you operate at the block layer or the file system layer, or both? Oh, both, right? Because you need to find the file name.
Well, first of all, back off.
Okay.
Ultimately,
when data is transferred to a disk, it is sectors. Now you may call them blocks, but in Linux, sometimes blocks are more than one sector.
Right.
Sometimes blocks correspond to page size. But the
groups,
disk
sectors,
doesn't
block
know
disks.
about that.
Right.
The disk knows about sectors.
Okay.
So at a higher level, the inode might have pointers to blocks, but the blocks are composed of multiple sectors. So you need to know that.
So it sounds like at least at first you guys are going to have recipes of known good like RAIN configs and file system configs.
Yeah, initially. Of course, if a customer comes up and says, I've got a Vertex system I want protected, then we'll help them either implement this kind of technology themselves for a Vertex system, or just turn it over to them and explain what needs to be done.
So if I wanted to use Lux on my host system, could I run a mapper? Right? Could I run a mapper after the fact to identify the sectors to my protected device here? Is that?
you can do that, yeah.
Well, I mean, how else are you going to get an encryption on the host?
How you get the information to it is up to the user. We will help with methods that we have used in our firmware.
And say, this is the way we've gotten the information to the mediator on sectors. If you have a different method that will identify the sectors assigned to files you want to protect, and then load those sectors to the mediator and say, I want these sectors protected, it will protect those sectors.
Okay, but like when you defrag or something like that, you're going to change the location, right?
You're gonna have to take care of that too. Sure.
I mean, do you have any niceties at all to help me with? I mean,
Not yet.
Okay.
No, not yet. No.
Okay.
Right now, we're more interested in providing the protections and getting it out there.
Okay. So now, memory mediator. So essentially, excuse me?
I think my dentist says one of those.
Yeah. So a memory mediator does the same types of operations as the disk mediator. However, our intent right now, and all right, so far, everything I've said so far has been funded and built to some extent and is undergoing testing, including the SATA mediator and although I haven't talked about it, the Ethernet mediator. The memory mediator is something that we are developing for a different application that has to do with embedded systems, but we are pushing to implement a memory mediator for the PC. And what essentially that does is it says I can reach in to my host memory independent of the I/O MMU or the processor MMU. So just a quick introduction to memory management units. Memory management units typically take a virtual address and emit the corresponding physical address. And they do this through things like page tables and page table entries. Okay? Something similar goes on through I/O MMU, so that the I/O, the DMA I/Os can be rerouted at execution time through these page table type entries. So, but we work at the physical level. That means we reach right into memory at the physical level. And in order to do that, what's needed is you need to understand the target processor's MMU, need to understand the target operating system's use of MMUs and where they are in memory. And then you take a copy of that information and do the mapping yourself on the coprocessor. And this is where something like the FPGA comes in, if you want to do it quickly. But in addition to that, like the disk, the memory mediator can be, has additional logic that can be primed for certain accesses. So that I don't want to waste a lot of coprocessor cycles checking memory for changes in significant data structures. In Linux, it's the significant data structure might be the process descriptor tables. It's a doubly linked list of process descriptors that contains all the information of executing processes. Well, I don't want to continually scan that where very often nothing changes. However, when something does change, I know where those process descriptor tables live, so I want to prime my mediator to yank on an interrupt line when that happens, so that the coprocessor does not waste its execution cycles checking for things that very rarely change. When they change, then I look. And so you can see that it's important to make use of that capability to understand your target OS at a significant depth. So this is not for household use. It needs a support staff, and there has to be something worth protecting at this level. Something that comes to mind is, Renaissance Technologies, that they want to protect their algorithms. Another thing that the government is very invests a lot of money in is these nuclear blast simulators. It's very expensive to develop that. It saves a lot of money, and those algorithms have got to be protected closely. So it's a machine that runs something like that is worth this kind of investment.